Good afternoon, everyone. Welcome to the Data Science Seminar from the University of Washington eScience Institute. Today is the last session of our mini-series of talks featuring projects from our winter data science incubator program. Today, we have Cassia and collaborator Jacob Cohen from the UW School of Oceanography, and Eric Gagliano, PhD student from the Terrain Analysis and Cryosphere Observation Lab in the Department of Civil and Environmental Engineering. These are two talks back to back, so just like the last time, we will start with the first talk, followed by the Q&A, and then we will do the second talk, followed by Q&A. We will start with Cassia and Jacob, who will talk about their project that they developed at the Science Institute on characterizing the spatio-temporal evaluation of marine heat waves. The eScience Institute data science lead on this project was Dr. Valentina Staneva, and the science advisor was Dr. Luann Thompson. Before we begin, I would like to acknowledge the Coast Salish peoples of this land, the land which touches the shared waters of all tribes and bands within the Suquamish, Tulalip, and Muckleshoot nations. As usual, please use the Q&A button at the bottom of the screen to ask questions. And with that, please, Cassia or Jacob, take it away. Thank you.
Thank you for the introduction. So I'm Jacob, and Cassia and I today will be presenting on tracking and characterizing the evolution of marine heat waves. And we want to thank both Luann and Valentina for their help on this project. So we're going to start with just the basic question, what is a marine heat wave? We know not everyone on the Zoom call is an oceanographer. So a recent paper came out just last week by Dylan and Amaya, actually really tried to define these different events really clearly. So their definition is a marine heat wave is an ocean temperature change that is transient and extremely warm relative to the expected conditions for a given place and time, as defined by an evolving recent climatological reference period. So marine heat waves are extreme events relative to both the long-term climate change signal, so this long-term linear trend, as well as a seasonal cycle. And they're extreme events above these expected cycles. So on the bottom here, I'm showing just a snapshot of actually yesterday's sea surface temperatures around the globe. And we can see that in some places, the water is blue or colder than expected. And in a lot of other places, it is yellow and red or warmer than expected by the climatological reference. A cool way to visualize what these heat wave events look like is this graph of sea surface temperature at a given location. So the blue line at the bottom shows the climatological reference values, and this is that seasonal cycle plus the long-term trend that I was mentioning. The black dashed line is a threshold value for extreme temperatures. We often use a 95% threshold value. So anything above that is considered a heat spike. And when a heat spike lasts longer than 5 days, then that whole event is deemed a marine heat wave. And we can see in the red line that represents the actual SST or sea surface temperature at this location. And in the middle and end of this period chosen here, the sea surface temperature exceeds the 95th percentile, and that is a marine heat wave. So a variety of processes in both the ocean and the atmosphere can lead to the evolution of marine heat waves. So we look at the ocean surface mix layer, which is the upper layer of the ocean that interacts both with the atmosphere above it and the cooler ocean beneath it. So processes in the ocean, like mixing, when those processes lead to less mixing between the mix layer and the colder ocean beneath it, then the mix layer can heat up. And things in the atmosphere like reduced cloud cover can lead to more incoming solar radiation that heats up the upper ocean. as well as things like weaker winds that will lead to less evaporation and less surface heat flux from the ocean to the atmosphere. So all of these different processes can contribute to the creation and evolution of extreme temperatures at the surface of the ocean. So marine heat waves are important to study for a number of reasons. Really important are ecosystem disruptions. So marine heat waves have been linked to toxic algal blooms along coasts, and additionally have been linked to die-offs of different fish species and seabirds. And these ecosystem disruptions also are related to economic disruptions in industries such as the fisheries industries. Additionally, with this long-term trend of a warming ocean due to anthropogenic climate change, the shifting baseline means that these extreme events are going to be warmer as the climate becomes warmer at its base. So these extreme events may have even more dire impacts on ecosystems and on the coasts of or wherever these marine heat waves are happening in a warmer climate. So we can ask, what is the impact of extreme events in a warmer climate, and how does that change? There are also local impacts of marine heat waves. As we can see in these two plots, I'm showing two recent marine heat waves that occurred off the coast of the Pacific Northwest and the west coast of the United States. So in September 2014, and really from early 2014 through 2016, a really large marine heat wave occurred that is known as the blob. And this had a lot of those ecosystem impacts that I mentioned before. A similar pattern of sea surface temperatures reappeared in 2019 and had similar negative impacts on the coast. And in 2014, when this occurred, I found one article that just said the Pacific Ocean may have entered a new warm phase. Consequences could be dramatic. By 2019, we were much more familiar with marine heat waves, and especially this blob-like pattern. And this was national news when the blob reappeared in 2019, and a lot of people were focused on what the impacts of this event would be.
So this leads to some of our questions as we try to understand the physics of marine heat waves by comparing them. And so here are several. First, how are marine heat wave events connected to each other? So marine heat wave spatial connectivity and temporal behavior can have different characteristics in different areas of the ocean. And most previous marine heat wave studies apply a case study approach where marine heat waves are treated as individual events. However, it has been shown that some marine heat waves, such as mid-latitude heat waves in the Indian and Pacific Oceans, are connected in space and time to each other through the tropics. And so can we find patterns of marine heat wave events? And finally, what can we learn from the interconnectedness of these events? And so to answer some of these questions, we need to develop a framework to understand marine heat wave diversity. Next slide, please. So I have applied a novel approach of tracking and identifying marine heat waves using the morphological image processing Python package OSTRAC, which was also developed in the Thompson group by previous grad student Hilary Scannell. And I'm working with a large and modifiable data set of marine heat wave events. The goal of OSTRAC is to serve as an approach for tracking the evolution of marine heat waves. And so by tracking, I mean identifying and extracting. So where candidate marine heat wave grid points are defined in detrended gridded sea surface temperature data using a seasonally varying temperature threshold, and that threshold is user defined. So identified marine heat wave points are collected into spatially distinct objects using edge detection, and then these heat wave objects are then followed in space and time while allowing features to split and merge. And the goal of our eScience incubator project is to develop an analysis package that would then naturally serve as an extension to OSTRAC, and it would also allow us to streamline our analysis. Our paper presenting OSTRAC is currently in progress, so it's not out yet. Next slide, please. And so coming into the incubator, our objectives of the study in collaboration with the eScience Institute were twofold. So first, we wanted to develop new methods of grouping marine heat wave events, and also to extend OSTRAC specifically by developing a package that uses OSTRAC output, picks features, and generates clusters of marine heat wave events. So our larger science goals were that we wanted to generate statistics for marine heat wave groups, which would then allow us to examine the global and regional scale drivers of sea surface temperature extremes. We also wanted to have an easily replicable analysis for one, different regions of the ocean, and two, using different data sets. Next slide, please. So our incubator goals were first to develop a library of marine heat wave metrics, second, develop a pipeline to streamline our analysis, and third, to parallelize the processing steps. Next slide, please. So first, developing a library of marine heat wave metrics. Next slide. So coming into the incubator, I wasn't really sure what sorts of metrics I wanted or needed. I kind of knew that I wanted a way to describe the events. And so in the figure here, I'm showing histograms and scatter plots of several metrics, the maximum intensity, duration, and total area. And we see that there is a range of intensities, durations, and spatial extents. And some of the major events in the past have been spotlighted. So here we see the blob, and then we see an event in the Mediterranean Sea as well as two others. And then some other metrics that I brainstormed include displacement, which would give us some information about movement, so zonal versus meridional, eastward versus westward. And another is the centers of mass. And then some of these metrics are one-dimensional, some are not. So instead, we might have a time series, and some are images. So these would all need to be stored differently. Next slide, please. Next, we develop a pipeline for analysis. Next slide, please. So we knew that we wanted to work with OSTRAC output, and the output looks like this, where our labeled objects are variables in an X-array data set. Next slide, please. We then combine the OSTRAC output with our sea surface temperature fields and our sea surface temperature anomaly fields, which is now another X-array data set. Next slide, please. And that is the input into our metrics package. So our general idea of how we wanted our pipeline to be is first we use as inputs tracked blobby objects. So that's an X-array with several variables. And then three types of measures are then calculated. So first, scalar values. Second, values that take into consideration marine heat wave time steps. So these are time series. And third, images. We then have a pipeline where some or all of the characteristics are used to generate some statistic about the marine heat waves. And we also spend a little bit of time visualizing some of our outcomes. Next slide, please. So third, we parallelize our processing steps. Next slide, please. So we spent some time trying to parallelize. We worked on NCAR's Casper cluster, so we had access to large memory, multi-GPU, and high throughput computing nodes, and initially tried using a SAS cluster to calculate metrics in parallel and experimented with different cluster specifications. And in theory, this is the ideal case, as OSTRAC also uses DASC under the hood. However, we had some trouble, and I still don't really understand it. So we decided to switch to joblib, which is a lot simpler, as time scaled with the number of workers, and it uses CPUs instead. And then we also used shared memory. And as a side note, perhaps we should have tried to parallelize running OSTRAC on multiple climate simulations first, as that is the main bottleneck. Next slide, please. We spent a little bit of time on visualization. So what do these heat waves look like in time and space? Here I'm showing a simple 3D volume plot using Plotly, where we have an axis for latitude, an axis for longitude, and an axis for time. So time is in months. Ideally, this would be a large rectangular box with all our time steps and heat waves scattered throughout. But we ran into some memory problems and tried rendering fewer surfaces. And in the future, we might try moving forward using PyVista instead. Next slide, please. We also spent a little bit of time doing dimensionality reduction. So here I'm showing, or we used TSNE and then projected on 2D and wanted to see the images themselves. We also tried PCA, but TSNE allowed us to see the separation better. The caveat here is that we might start seeing patterns that aren't real or that we don't understand. So here I've used the images of mean intensities, and we see that there is a clear El Nino signal in the ones that I'm showing. In some other heat waves, we might see a strong Central Pacific signal, so that signal would look different from this one. And so this leads us back to some of our larger science goals. This is an aspect of the project we want to explore more. So maybe work with a subset of heat waves, maybe by ocean basin. Next slide, please. And here we came up with a short wish list for the project. So we want to do more testing. We need to come up with a name and maybe try working with different atmospheric fields. And also include a pre-OSTRAC step where anomalies are computed using different methods. Next slide, please.
So Cassia and I have both been using both OSTRAC and this metrics package to look at two different research questions. So Cassia is going to talk about characterizing marine heat waves in the Northeast Pacific Ocean, and then I will talk about predicting the spatio-temporal evolution of marine heat waves.
My application is characterizing marine heat waves in the Northeast Pacific Ocean. So we have 3 guiding questions for this application. First, can we characterize marine heat waves with an imprint in the Northeast Pacific Ocean? How? Second, how unusual / extraordinary is the blob? So as you might recall, the blob is in the Northeast Pacific Ocean, and it was really strong in 2014 and also 2019. And my third question is, what is the impact of El Nino variability on marine heat waves in the Northeast Pacific? Now, the solution is to track, measure, and visualize marine heat waves with an imprint in the Northeast Pacific using a large ensemble of climate simulations. Next slide, please. So by a large ensemble of climate simulations, I mean the CESM2 large ensemble. And that consists of 100 ensemble members at 1 degree resolution on a regular grid. So in this figure, I've plotted the ensemble mean sea surface temperature, or the ensemble mean global sea surface temperature, and also the global mean sea surface temperatures for each of the ensemble members. And here we see that there is variation. So the point is that each model simulation is slightly different from one another. And so therefore we would be working with a large set of marine heat wave events, even if we are working within a bounded region, and that region is the Northeast Pacific Ocean. And now Jacob will go into greater detail into the other applications.
So my research project is working on predicting the spatio-temporal evolution of marine heat waves. And the 2 driving questions are, what would our predictions of the blob have looked like as it developed? And how can we use that knowledge to predict the evolution of the next blob-like event? Similarly, our solution is to track, measure, and visualize the blob in hindcast simulations. As an introduction, a hindcast is, I like to think of it like a forecast, but as we would have forecasted at a given time. So this schematic shows our observations in black. So that's what we know and what actually happened. The blue forecast at the end is what we could predict into the future using a climate model. And the red lines show what hindcasts predict from those previous points of initialization. So essentially, we take our conditions from a given time and then initiate climate models forward to see what we could have predicted and how that compares to what actually happened. So for this project, I'm using the data from the seasonal to multi-year large ensemble, or SMILE, prediction system. And this consists of 2 parts. So first is a SMILE forced ocean sea ice, or FOSSI simulation, which is a ocean model that is forced by atmospheric conditions. So it replicates the actual conditions from 1979 to 2019. So that's essentially our ground truth. And then every 3 months over that 50-year period, they have initialized 20 ensembles of 2-year model simulations. So we end up with 2 model years per simulation, 20 simulations for each of those initializations. 4 initializations per year, and 50 years of data, which ends up giving us 8,000 model years. So this is really a big data problem as well. So my first step was to visualize the blob in this Smile Fossey simulation, so these real conditions. And here you can see the evolution of the blob from December 2013 all the way through 2016. And we see that it reaches the Pacific coast of North America in late 2014, and the signal eventually reaches the whole Pacific Ocean basin throughout its lifetime. So currently, a lot of the prediction of marine heat waves is being done at the NOAA Physical Science Laboratory. Here I'm showing their current forecasts, which you can find online at this QR code if you're interested, or at that URL. And what this is the probability at each point in the ocean of there being a marine heat wave at a given month. And what we can see is some places are going to surely have marine heat waves. As you go out further in the forecast, these probabilities will decrease. What I'm interested in is moving from this point-wise prediction system where we predict the probability at every point to a more holistic view of a prediction where we can predict these whole events and their full life cycles. So we can use both OSTRAC and the measurements or metrics package to track the evolution of predicted heat waves in each of these ensemble members at different lead times to see how we could predict the full evolution of different events. So we'll leave with some takeaways. First, marine heat waves are complex to study, so it can help to look at them with a different view as connected events. And both OSTRAC and our metrics package allow us to track these marine heat wave statistics through this lens. Some next steps for the packages are to extend them to be able to track subsurface heat anomalies. Hilary Scannell, the former grad student who created OSTRAC, had a paper about the subsurface imprint of the blob. So it'd be interesting to apply OSTRAC to those anomalies as well. We also are interested in extending these Python packages to work with different time resolutions like daily data, as well as with irregular grids, because the ocean models themselves are not on just a strict latitude longitude grid. So currently OSTRAC does not work with them. But we're excited to keep moving forward with these packages, and we'd be happy to answer any questions.
Well, thank you so much. That was great. Please use the Q&A button to ask questions. Here's one. Or not. I'm not sure. Oh, yes, very cool. Work using a large variety of different techniques. Sorry if I missed it, but what were your anomaly detection methods?
So it varies by data set. OSTRAC works on the anomalies already. So for example, for the observational data, we're mostly using monthly data. So we take out the linear long-term trend and remove both the annual and semi-annual harmonics to get rid of a seasonal cycle. And from there, those are our anomalies.
Thank you, Jacob. I was curious about those metrics too. Like you talk about intensity, duration, total area. I was wondering what types of methods you use to identify, for example, the intensity. You use a threshold method for the duration, a duration threshold, or like for area. How do you identify these events?
Jacob, do you mind going back to the metrics slide or the characteristics slide?
Yeah. Oh, oops. Sorry.
Okay, so So the way that OSTRAC itself works is that you can set a threshold for your radius, so the size of your object. And the output of OSTRAC is these like labeled blobby objects. So you already have kind of what you want to work with. And so for example, if we wanted to get the duration, I just count the number of time steps that a certain label appears. Does that make sense?
Yeah, thank you. Here's one more question in the Q&A. Yeah, if you want to go forward, yeah, go ahead.
Oh, we can move on to the next question.
So this question refers to very cool, wanted to understand if it's completely empirical work using ensemble methods, or do you use some basic analytical math model?
Right, we just use ensemble simulations right now. Yes.
Yeah, I'm not sure I understood the question.
So yeah, I think it refers to a if you're using simulations or some basic analytical model.
Oh yeah, we're just using simulations.
Yeah, and we didn't run these simulations. We're just accessing the data from these.
Right. Here's maybe this is the last question we take. Here's another one. Okay. We're taking these two and then we're gonna move on to the next presenter. One refers to the package and how the package handles labeling blobs, if it split apart or merged together.
Okay, yeah, so the way that OSTRAC handles labeling blobs that's split. So for example, you might start with a blob that is like not split, it's one blob, and at some point it splits. So I think it's wherever it touches, or if it like connects, it's seen as the same object. I don't know if you want to add something, Jacob.
Yeah, I can try to add to that. Just actually maybe this one might help. So yeah, essentially like it does this labeling at every time step and then looks at it in essentially this 3D sense, and anywhere that like one object may be touching, anything connected to that touching point will be connected. So if two events start and then merge and then split, that's all considered one event.
Thank you. And one last suggestion from David, did you try casting to flow 32 to alleviate some of the memory issues?
No, I did not try, but that is a great suggestion. I think I might.
Excellent. Thank you. Thank you for your suggestions and questions, and thank you for presenting this. And now we're going to switch over to Eric.
Okay, let me just pull up my slides real quick. Okay, are you all able to see and hear me well?
Yes.
Okay. So hi everyone, my name is Eric Gagliano, and I'm a third-year PhD student advised by David Sheen in Civil and Environmental Engineering, and I study ice and snow using satellite radar. I'll be presenting my incubator work, which focuses on understanding large-scale snowmelt timing using satellite data. And we collaborated with our data science lead and resident expert in all things geospatial, Scott Henderson. So I'd like to start with a bit of background on snowmelt timing and why it's important. But first, we'll take a step back and talk about snow. Snow is frozen precipitation that falls in the forms of flakes. And depending on where you live, you may or may not have seen it before. Seasonal snow, which is snow that accumulates during winter and melts during the spring, plays an essential role in the Earth system, such as reflecting solar radiation, effectively cooling the Earth when you, which you can see on the figure on the right. And more than 1/6 of the world's population relies on runoff from seasonal snow and glaciers for agricultural and domestic water supply. So in a way, snowpack acts as a huge water tower that builds up in the winter and releases when it gets warmer. So let's take a quick peek at how snow cover changes throughout the year. I'll start this video, goes pretty fast, but we start in September and can see how snow progressively makes it to the lower latitudes. And snow mostly occurs in the northern hemisphere, and snow cover peaks around February, March-ish. As temperatures warm, we see the snow cover retreat north again, and the cycle continues. So most of that snow that you see disappear in the animation during the spring melts, and it's important for us to know specifically when this snowmelt actually occurs. Let me give you two big reasons you should care about snowmelt timing. Reason one is that snowmelt timing regulates the release of meltwater, which has important implications for downstream water resource applications, flood risk management, and ecosystem maintenance. As we mentioned, over 1 billion people rely on snow as a water resource, so it's really important to know when the snow turns into water. Reason two is snowmelt timing is often used as a common indicator of regional climate change. On the plot, you'll see observed changes in the timing of peak snowpack from 1982 to 2020. Locations where snowpack is peaking earlier in the year appear in pink, and locations where snowpack is peaking later in the year appear in green. The study that this plot comes from found that in the Western US, there is a trend towards earlier peak snowpack at 84% of the analyzed sites, with an average shift of 8 days earlier in the years since 1982. And for the Western US, snowmelt timing is projected to advance earlier in the year by up to 1 month by 2050. An earlier snowmelt combined with trends for lower snowpack totals across the board is troubling for those that rely on meltwater in spring and summer. So the snowmelt runoff onset date, which is the date at which water begins to leave the supersaturated snowpack and flow into rivers and lakes, is particularly important to us because it dictates both the beginning of increased water availability and the rate of spring flow. High-resolution maps of snowmelt runoff onset date will enable more accurate water resource forecasting and regional climate analysis. Due to the high sensitivity of microwave radiation to liquid water and snowpack, radar remote sensing has proven useful to delineate between different snowmelt phases. Radar instruments on satellites offer high spatial and temporal resolution measurements, which can be used to create estimates of snowmelt runoff on a global scale. However, no global radar-derived runoff onset maps are currently available. I'm sure you see where this is going. In comes synthetic aperture radar. Synthetic aperture radar, or what we'll call SAR for the rest of the presentation, is an active remote sensing technique that utilizes the movement of a sensor platform to create a synthetic aperture for finer spatial resolution imaging. That's a lot, and the exact mechanics are a bit more complicated than that, but for our purposes, it's not really too important. But SAR is awesome, and there are a lot of great applications that we don't have time to get into. We are particularly interested in using SAR to better understand snowmelt dynamics, as SAR is sensitive to the dielectric properties of snow, and snowmelt processes have distinct dielectric signatures. So here's a time series of SAR images over Mount Rainier. The values you're seeing is radar signal returned to the sensor, which we call backscatter. Brighter values mean higher backscatter, and darker values mean lower backscatter. Notice as temperature warms up and snow begins to melt, we see darker colors or lower backscatter starting from the lower elevations because the presence of liquid water in the snowpack reduces the amount of backscatter returned. The time series lets you visualize how snowmelt progresses up the mountain as the melt season continues. So during the first few years of my PhD, we developed and released an open source toolbox to explore cloud-hosted publicly available Sentinel-1 C-band SAR data and produce snowmelt runoff estimates. That's a bit of a mouthful, so we'll break it down a bit. Sentinel-1 is a set of 2 satellites that have an exact repeat interval of 12 days and have some pretty cool uses. C-band radar just refers to the specific wavelength of microwave radiation that the radar instrument transmits to the surface. And to date, I've primarily focused on analyzing time series for smaller sites. including the Cascade Range stratovolcanoes, which you can see the maps here on the figure on the left-hand side. My results were promising, and I've been able to not only produce these snowmelt runoff onset maps, but also analyze the topographic and meteorological controls on runoff timing with the aid of digital elevation models, automated weather stations, and stream gauge data. We've been using these data to study the key forcing parameters of snowmelt runoff onset at high resolution, which are currently poorly understood in mountainous areas. We hope to scale up our methods to create snowmelt timing products on a regional to global scale. These products would be valuable for, among others, water resource managers and climate scientists. The objective of this incubator project is to scale up the processing of these snowmelt runoff onset maps beyond the current watershed and mountain scale. Our primary goal was to process the full Sentinel-1 catalog, which began in 2014 and continues to the present, to prepare seasonal snowmelt runoff onset maps for the Western US, with a final stretch goal of building the infrastructure to process the entire globe. And so the method that we developed prepares and analyzes a time series stack of Sentinel-1 images for a year and locates the temporal radar backscatter minima at each pixel location. Due to the dielectric properties of water and snowpack, the date a pixel reaches its temporal minimum corresponds to when water completely saturates the snowpack and runoff onset begins at that pixel. So let's walk through this figure on the right. This is Mount Baker in northern part of Washington. We start with the images from different orbits of the satellites, and each orbit being a different color. So you can see the reds, the orange, and the yellow. Then we build a backscatter time series of each pixel and estimate the timing of the backscatter minima at each orbit, represented by the dashed vertical lines. So this is the backscatter time series for each orbit, has its own color, and the dashed line corresponding to that color is just saying that's when the minima is happening. So we then aggregate, we take the median of these day of year estimates and find the median is day of year 115 for this pixel, which corresponds to April 25th. We place that date in the snowmelt runoff onset map for that pixel. And then we do that for every pixel to build up the entire snowmelt runoff onset map. As expected, in this bottom plot here, we see lower values corresponding to a runoff day in April-ish at the bottom of the mountain. These are the dark blues and purples. And higher values corresponding to a runoff onset day in June and July at the top of the mountain, the brighter colors. Now, where can't we apply this method? We would have a hard time estimating snowmelt timing in areas without snow, so we know we need to remove that. Also, the specific band radar that we use, C-band, has trouble penetrating tree cover, so we won't try to estimate below the tree canopy. So before we can apply this method globally and regionally, we need to have a way to remove these areas. And so we use a seasonal snow data set in order to remove these black areas that are little to no snow. And additionally, this is the world cover data set. It's a land cover classification map. And we use it to remove tree cover, water bodies, and buildings and infrastructure from our processing. So now we're only going to be looking at areas where we know snow should probably exist. Now, the ambitious scale of this project is hard to attempt on your typical laptop from 2016 with only 2 gigs of working RAM. I would know, I've tried that. So we make use of Microsoft's Planetary Computer Hub, a cloud computing platform tailored to working with geospatial data. An added benefit of using Microsoft Planetary Computer is that our Sentinel-1 dataset is hosted there. So doing our processing next to our data ensures a more efficient pipeline with less total data transfers and downloads. If you're interested in the numbers, Planetary Computer allows for scalable DAS clusters with up to 100 workers per cluster and 8 gigs of memory per worker. We use Python and related geospatial packages for our processing. And for processing efficiency, we settled on a scheme to process 100 kilometer by 100 kilometer tiles at a time which we can later stitch together to form our larger maps for the larger scale analysis. And for the Western US, we processed over 30,000 SAR images across 273 of these 100-kilometer by 100-kilometer tiles. And we had actually, I think this is a bit of an underestimate, but we had more than 100 terabytes of data to sort through. So let's check out the results. So to visualize our snowmelt runoff onset maps, we built this interactive map that you can access on the web. So scan the QR code if you'd like to check it out for yourself. It works pretty well on just your mobile phone. I was worried that if everyone is accessing the interactive map at the same time, it might crash it. So we recorded this on YouTube earlier so that we wouldn't run into any technical difficulties. So I think in this video, I'm about to click the link. Yeah, there we go. So this is a map of the Western US, and you can see the data being loaded in. This data is our 2015 to 2022 median snowmelt runoff onset map. And you can see the color bar at the top of the screen there. Similar to the method slide, the darkest blues represent earlier in the year. For this map, it's day of year 32, it's February 1st. And the brightest yellows represent later in the year. Day of year 23 is July 31st. So I'll just pause it here for a second. So we can zoom in on this area a little west of Lake Chelan in Washington. So you can see Glacier Peak over here. Notice that the mountainous regions have a later runoff onset. Keep this now. We observe earlier runoff dates on the southwest slopes of some of these mountains. So both the elevation control and aspect control on runoff onset seem to match our intuition in terms of elevation dependent temperatures and direction of solar radiations. So now I go through and click through some different layers. I have snowmelt maps for all of the full years for the Sentinel catalog. And notice the large shifts in runoff onset from year to year. We also have a couple of other metrics that we can look at, which happen a little bit. So for example, these reds are a measure of variability, interannual variability of snowmelt runoff onset. So the darker reds have the highest variability, and we see the lowest variability in the mountains with the whiter pixels, and the highest variability in the lower lying areas. We also have a short-term trend map, which is just for the 8-year record. And it just shows us whether we see snowmelt runoff onset advance or retreat in the year. So blue is actually advance later into the year, and red is earlier in the year. And then finally, we have these tiles, this tile scheme that we use. So if you were interested in processing a specific area, different resolutions, or using different polarizations, and you want to use our toolbox, you can go here and just pick up the tile that you think would be most useful to you. So that's the map. Let's try and understand how good our estimates are by comparing our product to some on-the-ground data from some weather stations. So we use the SNOTEL network, and the SNOTEL network is comprised of over 900 automated weather stations in the US. For our purposes, it's important to note that these are mostly in mountainous environments surrounded by trees. That'll be important later. These stations have a ton of sensors, some of which you can see in the labeled image to the right. And we're interested in the amount of snow at these stations. And the snow pillow sensor is a great place to get snow water equivalent data, which we'll call SWE. SWE is basically a way to measure the amount of snow in a snowpack, and it represents how much water is in the snowpack if we just torched it, we just melted it all. So before we talk about the results, let's talk about what we would expect. So we expect that the timing of maximum SWE from these SNOTEL stations should be close in proximity to the time of our snowmelt runoff onset estimates. This is because the greatest amount of water in the snowpack should occur right before the water starts to drain the snowpack. You can see some of the literature we cite here. So on this plot, SWE is in red, and radar backscatter is blue and green. And the diagram shows that when the backscatter minima is reached, which is right over here, the runoff onset initiates, and you can see the red, the SWE, begins to decrease. So let's start with a single SNOTEL station. And this is the station at Paradise in Washington, right by Mount Rainier. And we're looking at the 2018 melt season. So the plot on the bottom here shows our snowmelt runoff onset map with a red circle of radius 500 meters around the SNOTEL site. And we take the median of all valid pixels in the zone to get our estimated runoff onset at the station. Then we compare this date to the date of maximum SWE observed at the station. So up here, the blue dashed line is when the maximum SWE occurs, and this black line is our median estimate of runoff onset. And the black line is the median of all of these colorful greens and reds, which are the separate orbits, but that's not very important right now. But we observe an offset between the SNOTEL max SWE timing and our SAR-derived estimates of 9 days. You can see that in the gap right there. So let's look at the offsets across the rest of the SNOTEL network. And now that we have an underlying understanding of what happens at these single sites, we're going to validate against as many SNOTEL sites as we can. And here we compare the offsets of 550 SNOTEL sites. And here are the plots for the worst and best years of our estimates in terms of agreement with the timing of SNOTEL SWE. So on the left subplots, the orange is a histogram of SNOTEL max SWE timing with day of year on the x-axis, and the blues are our SAR-derived runoff estimates. And the subplots on the right show the pairwise offsets for all stations. For the last plot, that would have been like the 9-day offset that we saw. So some years there's high agreement, such as 2018, where the median offset between max SWE timing and SAR-derived runoff onset was only 4 days. 2015 is an especially bad year with a median offset of 16 days. So these can be wildly different year to year. But across all stations, there's a bias in our differences. SNOTEL max SWE often happens a week or two before we predict melt. And here's a plot of the SNOTEL locations with the color corresponding to the median absolute difference between max SNOTEL SWE timing and our SAR-derived runoff onset estimates for all 8 years of data. So brighter blues mean closer agreement, and pink means very poor agreement at these stations. So there's likely something wrong here. And these differences could be due to a couple things. But for now, we'll talk about some tree stuff. Even if our temporal resolution of SAR data was very high, we'd still have these issues at a handful of sites. So you can see this picture of a SNOTEL station, the Paradise station that we were talking about in the top right. And you can see it's surrounded by tree cover. And that's a bit of a problem for us because we've masked out our tree cover from our analysis. So there are less valid pixels you can see in this red circle area. And also for the valid pixels that did make it through, there could still be some tree cover in there that wasn't picked up by the land cover classification set. So there could be some uninterpretable C-band data there. And as well as snowmelt timing is possibly different between forested and non-forested areas in the same spot, in the same location. And we also have to consider that SNOTEL site locations are not always super accurate. That's by design. They don't want people going to town and having fun with these and using them as like monkey bars or something. And importantly, rain on snow events and diurnal snowmelt dynamics complicate our estimates and can cause false positive signals of runoff onset. So besides the fact that snowmelt timing has important downstream implications, here are the 3 big takeaways from today's presentation. We can build snowmelt runoff onset maps using radar imagery. We've built a scalable pipeline to process regional and global scale runoff onset maps. And there's decent agreement between our SAR-derived runoff estimates and weather stations. These 3 takeaways enable us to build large-scale data sets, which will help us answer important science questions going forward. Our next big task is to fine-tune our method to remove some artifacts that you may have noticed in the interactive visualization. After this is complete, we can run our pipeline globally. And from there, we get to the fun part and analyze these products to better understand the timing and spatial patterns of global snowmelt and answer some science questions. So as our data archive grows, a larger SAR record will allow us to identify longer-term trends and shifts in snowmelt timing. There are also other SAR-derived snow products that we're working on, such as snowmelt duration. And to improve our validation, we could try other methods and expand our validation data sets. There's also new SAR satellites on the way, each with different strengths. We hope to harness this new data to see beneath the tree canopy and also capture the diurnal evolution of snowmelt. And finally, we hope to make stakeholders aware of these data sets and tools and communicate our science results. So lots of work to be done there. So here's some QR codes if you're interested. They'll also be on this next slide. And with that, I just wanted to say thanks. Big thanks to the entire eScience team, especially those who work behind the scenes and make everything run smoothly and help build community. I always had a lovely time every time I went up to the penthouse, the eScience Data Science Studio. Wonderful group of people, and I hope I get to spend some more time there. And special thanks to Scott. If you ever get the chance to work with him, you got to do it. Scott is super knowledgeable with SAR and the latest advances in geospatial stuff, and Scott is an awesome mentor. And then thanks to my lab, David as always for guidance and motivation, and Seth for initial ideas and continued feedback on this project. And everyone for moral support, and everyone for attending as well. So thank you, and I'd love to hear questions if we still have time.
Excellent. Thank you so much, Eric. That's so awesome on so many levels. Scalable workflows, new sensor, being able to do analysis at a global scale, that's all very exciting. I think maybe I have a comment first. Please use the Q&A box to ask questions. One of the ideas that came to mind when you were talking is that 2015 was one of the exceptional dry years, speaking of snow. So that's an indication of perhaps how good this system will be able to identify the date of or snowmelt runoff during very low snow years. I'm hoping you will improve in the future, and with the multitude of sensors coming along, there's be more opportunities to assess your product, and also using perhaps the LiDAR-derived data that's available to look at different slopes and aspects, and perhaps quantify better the vegetation effects of on your product.
Yeah, for sure. And I think the 2015 snow drought is super interesting, and you can really see it in this record. And a lot of the actual discrepancy that I think actually comes from the SNOTEL comparison is it seems like there was barely any snow at these locations, so it's hard to have enough like signal to noise ratio to really pull out some signal there. So when we do the larger scale analysis, it would be great to look at 2015 specifically.
Excellent. Two questions. Here's one. Will this method work with NISAR data? Can you combine Sentinel-1 and NISAR backscatter data?
Yeah, I'm really excited to do that. So for those not aware, NISAR is a new SAR satellite that's going to be coming online hopefully next year. And it uses, instead of C-band like Sentinel-1, it uses L-band. So it's a bit longer wavelength. So because it's longer wavelength, it's able to penetrate tree cover better. And because of that, it'll help us find snowmelt timing and snowmelt properties underneath the trees, which is something that we can't currently do with Sentinel-1 reliably.
Great. We'll take one more question. Cool that you can process so much data. How long did it take? What kind of architecture?
So it really ended up being a matter of choosing some sort of resolution that we would have to be okay with. It's a trade-off to say, we want to be able to process in X amount of time, but only have like a certain spatial resolution. But we settled on 80 meter for now. This is something that we can improve in the future, but running on the DAS cluster on Microsoft Planetary Computer, we were able to get run times to process an entire 100-kilometer by 100-kilometer square in a matter of 30, 40 seconds, which is pretty good because then you can loop through a bunch of those squares, and you can imagine getting a global 80-meter coverage, given a week of running this. So
80 meters is great. I don't see other questions. And at this point, I would like to thank everybody for their participation in the incubator program and for sharing their results with us today. And of course, I take the opportunity to invite you to participate in our incubator program next year. With that, I'll say goodbye for now, and we'll see you next week.